Now we go through the stanchion, and here's the stanchion height. It's 7.4 meters long, height of our stanchion. We've derived the applied loads from our analysis. Our material properties and our section properties are the same as the rafter, so we just pull those down from above. A bending check for the stanchion. We've got a bending about the minor axis of 68 and a bending about the major axis of 444, as we saw before. Then we need to look in the buckling, and because we're going to restrain it with girts at third points, we can say that our girt spacing is 2.5, therefore our segment length is 2.5 meters. And the beta M value we can take from the table, because we're looking at the top third of a pinned-based stanchion, and we've got an alpha M of 1.18, which gives us a max span of 1.4. So that would suggest that we add our rotational factors, our twist factors, our load height factors. That comes out as 2.1. So it's telling me that it's unrestrained and buckling might be an issue. We derive our reference buckling moment as we did before, and our slenderness factor as we did before, and come out with a nominal member moment capacity as 458. So which is higher than our actual section capacity. So we check for shear as we did before. So because it's a stocky web, it's going to be about the shear capacity rather than the shear buckling capacity. Then we need to check our axial load. So again, we look at the slenderness limits, and we can compare those with the effective width we've actually got. And from that, we can derive our nominal section capacity. You see that's 2,373 kilonewtons. So it's a very large axial load capacity. That's if it's fully restrained. If we go through and look at the two directions, so when you're looking at an axial load, you need to consider both directions, i.e. minor axis and major axis. So we have restrained it at third points, but we've only restrained it about the minor axis. About the major axis, it is still unrestrained, and because it's a sway frame, you get a KE of 2.2. So that makes a big difference in the axial capacity of your stanchions in a pin-based portal frame. So you work out your slenderness reduction factors from clause 6.3, and that gives you a nominal member capacity of 14 and 10. So the slenderness limits are based on the maximum slenderness you get from the minor axis or the major axis. Now, in some cases, because of the differences of restraints you have, the major axis may be the problem rather than the minor axis. But for most of our universal beams, and given that you're probably putting girts on your columns, you probably find that it's your minor axis. Depends. Again, looking at combined actions for the loading of the stanchion, as we've done before for the rafter, and we get to our final capacity. A quick look at the stanchion restraint, and we've got our restraint provided by panels, and the limitation is actually the bearing within the panel. So we need 4 bolts to connect our stanchion restraint to that column. Finally, looking at the deflection. Now, often portal frames, particularly skinny ones, are dependent upon deflection. They're almost governed by deflection at serviceability limit state. And we've gone originally with our pinned base portal frame design and found our deflections to be rather large. So there is a paper from the Steel Construction New Zealand report Gen 7001, and that talks about base fixity, and the base fixity can be partial. So sometimes you can go somewhere between fully fixed and fully pinned and put a spring in there. So for SLS loading, it recommends a value of 0.8 EI over H, which gives us a rotational stiffness of 6,387 kilonewton meters. So that gives us your limit there. Just faded out there is a similar one for ultimate limit state at 0.4 for ultimate limit state. The thing to note is if you are putting spring bases in, you are going to attract moment at your bases, and therefore your foundation needs to be designed for that moment. And there are not many simple pad foundations that can take the moment you're putting it in at ultimate limit state, whereas at the serviceability limit state, it can probably quite happily survive. So given that our portal spacing is at 7.5 meters and our portal height is at 7.4, the suggested limit on the sway deflection is the smaller 2 versus 200. So our limit is going to be 37 millimeters. From our multi-frame analysis with a spring base, we get down to 25 or 27 in the case of earthquakes, which in either case is quite adequate.